Hey guys, how are you? It's Mrs. Lasner just checking in and wanting to say hello. I miss you guys so much and I just want to pinch all your little cheeks. I know you're not little kids anymore, but I miss you. Anyways, so I just decided to record a little video going through one of the harder FRQs from the testing year of 2011 because since then a question of that type has appeared. It appeared in 2012 and again 2017. So I wanted to go through it with you and then have you practice the ones from 2012 and 2017 just in case a question of that type appears on this year's test, you would be ready for it. So hopefully you find the video helpful and let me know if you have any questions about any of the ones you have to practice or even about the one in this video. Okay, hope you enjoy. Hope to see you soon. Bye.
Okay, so let's get to it. AP Review Day 1. So it begins. Now, this is the question here that I was referring to from 2011. What made it harder and different than any other previously given separable differential equation is that in the derivative, which you see here, this is the derivative of w with respect to t. In that derivative, there is no variable t. So it was the first time they had a separable differential equation with only the dependent variable in the derivative and not both the dependent and independent variable, which can be really counterintuitive and just odd. Now, one thing I want to point out is what W represents, because we're going to be talking about W a lot. And so W is modeling the total amount of solid waste stored in a landfill. And it's measured in tons, and it's with respect to T, and that is measured in years from 2010, from the start of 2010. So it's a good idea for us to wrap our head around all of these variables and what they represent, and then what units they are being measured in. Okay, so part A tells me to use the line tangent to the graph of W when T is 0, okay? So it's a line tangent to W at t equals 0. And then we're going to use that line to approximate W, right? Amount of solid waste, that's W. We're going to use the line to approximate a value of W after 3 months have passed. So the first 3 months of 2010, and then they tell us here, t is equal to 1/4. Okay, so why is that? Why would t equal 1/4? That goes back to the fact that t is measured in years from the beginning, the start of 2010. So if 3 months have passed, that would represent 1/4 of a year since the beginning of 2010. So let's, wrap our head around all of that. Okay, but the line is tangent at t equals 0. So we're going to make a line tangent at this point and then use that line to evaluate what W would be at this point. So as a quick reminder, linear approximations follow this formula. The y value at the given, or the dependent variable value at the given x value or independent variable value, right? So this is just a point on the graph when t is 0, added to the slope of the tangent line, or the derivative of y at the given x, which in this case would be the derivative of w when t is 0, times x minus the given x, which in this case would be t, minus 0, which is my given value for t in this situation. It follows this formula. That was the formula we had been given back in chapter 3. And then I'm applying it here to this context. The y is w and the c, the given x value or the given t value, is 0. And so there you go. So let's do the work down here. Well, the question is, what is w of 0? I don't have an equation for w, so I need to go back up to the beginning of this problem to get some more information. Now remember, 0 means the beginning of 2010, right? Because t represents years from the start of 2010. So this would be 0 years from the start of 2010, the beginning of 2010. So right here, it tells me at the beginning of 2010, that's exactly when t equals 0, the landfill contained 1,400 tons of solid waste. So that right there is the value of W, right? W is the total amount of solid waste, so 1,400 tons of solid waste at the beginning of 2010. So W of 0 is 1,400. And now I'm just noticing it says it right here in front of my face. I didn't see that at first. Anyway, we got the value for W of 0. Then comes another challenge of finding W prime of 0, derivative of W at 0. Well, I am given the one way of interpreting the derivative of W, and that is dW dt. So that means the same thing as W prime of t. Maybe I'll write that here. W prime of t is equal to dW dt. So W prime of 0 would equal dW dt evaluated at t equals 0. The only problem with that, or the slight complication with that, is that there is no t in the formula for dW dt. There's only a W. So I have to figure out what I need to plug in then. Well, we just found out a second ago that when t is 0, W is 1,400, right? So that's what I plug in for W in my derivative, right? My derivative is 1 over 25 times W minus 300. And when t is 0, that W is 1,400. Okay, so then this is 1 over 25 times 1,400 minus 300, which is 1,100. And then 1 over 25 times 1,100 gives me 44. So that is the value of W prime of 0. That's what the derivative of W with respect to t equals at the point in time when t is 0, because at the point in time when t is 0, W is 1,400. So we found that. Now my tangent line will equal my initial value, or my value of W at 0, plus my derivative, my rate of change of W at 0 times t minus 0, so just times t, right? Because t minus 0 is just t. So there's my tangent line. Now what I want to do, and this is going to approximate my actual value of W. And so what I want to do is figure out what the amount of solid waste is after 3 months have passed, which would be when time is 1/4. So it'd be 1,400 plus 44 times 1/4, which is 1,400 plus 11, which is 1,411 tons, right? This is the approximate value for W of 1/4. Not the exact value, but it gives us an idea of how much waste would approximately be there. Let's check real quick with the scoring guidelines for Part A. So here are the scoring guidelines for Part A, and you can see that they decided to award 1 point for finding what the derivative equaled when t is 0, because as you know, that is not easy to do. That was a really tricky thing. So that was where we had to figure out what the derivative would equal when t is 0, even though there's no t in the derivative. They wrote it here as W of 0, and actually that's really helpful to see that when I plugged in 1,400 for W, it's because that's the value of W at 0. So this is the way of evaluating the derivative when t is 0. And they got 44. So you get 1 point for finding the 44. They didn't award any point for the tangent line, which I find interesting. They were probably saving up all their points for Part C, because I feel like that in of itself should get a point. But anyway, you got 1 point for finding the derivative, and then 1 point for the answer, which was the 1,411 tons. So far, we've gotten 2 points from this problem. So we can just check that off. We got 2 points there. Okay, so now we move to Part B. Part B, I believe we did before. I can't remember when, but when we were learning about proving whether something is an overestimate versus an underestimate. This goes back to, I believe, Chapter 3 again. Finding linearizations. Okay, so they want us to first find the second derivative of W and then use it to prove whether or not the estimate we just found, the 1,411 tons, is an over or underestimate of the true amount of waste at time 1/4. So let's go ahead and work through that. Well, it might help to remember that the second derivative is just the derivative of the first derivative. And this is the first derivative right here, which is weird. It's not in terms of t, but that's okay. We'll survive. So I'm just going to take the derivative of both sides with respect to t. So dw dt, the derivative of that is the second derivative, d squared w over dt squared. I'm going to apply the constant multiple rule, right? So this is just a constant right here, the 1 over 25. So you just multiply that to the derivative of the function, w minus 300. So the derivative of that would just be dw dt minus 0, because the derivative of 300 is 0. And since this was w and not t, the derivative of this is not 1, but it's dw dt. It's kind of like implicit differentiation, sort of. So that's the derivative. And you might be thinking, that's so weird. That's like nothing. That's just like using names for things, and you would be correct. But we do know what dw dt is, because they give us the formula for it right here. So I can take that and sub it in the place of dw dt. So then I get 1 over 25 times all of this again, right? 1 over 25 times w minus 300, because that is what dw dt equals, right? I'm just plugging that in, substituting that in for dw dt. And then if I simplify that, it equals 1 over 625 times w minus 300. So that is equal to our second derivative with respect to time. And again, it's weird because only w is in the second derivative as well. So that's that. And now what we have to do is use this to determine whether our estimate back here in part A is over or under. So what we really need to do is figure out whether this second derivative is positive or negative. That's what I need to figure out. And not just anywhere, but like specifically at the values of t that we've been interested in. So this tangent line was found when t was 0. So, and then it was used to approximate when t was 1/4. So really the interval I'm most interested in is between 0 and 1/4, the point of tangency and then the point where I approximated. On that interval, is this derivative positive or negative? Well, when t was 0, then w equaled 1400, which is greater than 300. And when t was 1/4, then w was a little bit more than that, right? Because w is an increasing function. I believe it did mention that somewhere earlier. It went up. It's increasing, not decreasing. So that would also be greater than 300. So what we can figure out from that is that the second derivative is going to be positive. So 1 over 625 times w minus 300 will be greater than 0 because the values of w are bigger than 300. So when I subtract, I'm going to end up with a value that's positive. So the second derivative is greater than 0 for values of t that are between 0 and 1/4, which means that w itself, right, this is the second derivative. So if I go back to antiderivatives, w itself will be concave up on the interval from 0 to 1/4, because its second derivative is positive on that interval, so it itself will be concave up. So really quick picture of what that means. So let's just picture something that's going concave up, right? Let's say this is our point of tangency, right, where t is 0, and then where we approximated would be a little bit to the right of that, where t is 1/4. So here's my point of tangency right there at t equals 0, and I approximated at t equals 1/4. Because the graph is concave up, the tangent line is forced to lie below the curve, so the approximation would be under, less than the true value, right? The approximation's on the line, the true value is on the curve, approximation is below. So we can make that conclusion. Since this means that w is concave up, therefore our estimate is an under estimate of the true value. Of w of 1/4. So there would actually be even more waste than 1411 tons at that time. So let's check that with the scoring guidelines as well. So for part B, they gave 1 point for finding the second derivative because they asked you to. So when they say find something, you know that's going to be worth a point. And here's the process that we went through, right? 1 over 25 times dw dt, sub in 1 over 25 times w minus 300 for dw dt, and you get this, and that's worth 1 point. And then 1 point for the answer with the reason. So you only get the point if you explain. Therefore, the second derivative is positive. You just mentioned that. So therefore, our answer is an underestimate. So they were saving all the points for part C. Part C is going to be worth a whopping 5 points. Because remember, FRQs are always out of 9 points total. So we had 2 points for part A, 2 points for part B. That's 4, leaves 5 for part C. And that's because that's where they want you to find the particular solution. So I'm going to clear some space out because I think I took up all my room here. So let me erase and let's go ahead and do part C. But I want to point out one thing, because another thing students often mess up on when they see a question like this where they give you a derivative and then they ask you to use the line tangent to W, which is the antiderivative. A lot of times in part A, students will go, oh, I need to find W in order to get the tangent line to it. And the answer is no, actually you don't. To find a tangent line, you just need one value of W and one value of its derivative. So when you're given the derivative and then like other information about that function at one point, that's all you need to get that tangent line. You don't need to actually find W. The only time you actually have to find W is when they're telling you find W. Right there. Okay. So now let's go ahead and do that. So we start by setting up our derivative. And then the first step, the most important step, the step that if you skip it, you'll lose all of those 5 points is, I hope you're all saying it right now, separate the variables. You might be going, but Ms. Lazarus, there's only one variable. There's nothing to separate. And I would say, well, that's wrong because there's one here and here, right? There is a t in there. It's just a dt instead of a regular t. So, but this is still weird. It's super weird. So here's what we're going to do. We're going to divide by this whole entire quantity. Okay, divide by that because I want that on the side with dw. And then the dt, we're going to multiply to the other side because I have to like cancel it out from where it is now. So it's in the denominator. Technically, it's being divided by dw. So to separate it from dw, I'll have to multiply it. Meanwhile, w minus 300 is technically in the numerator, and so I need to divide it to move it to the other side. Now, one thing I'll say about the constant is if you ever have a situation like this, it makes more sense to keep the constant on the side where dt will be, because that way you won't have to use like a u substitution or something on the other side. Okay, so that would look something like this. dw divided by w minus 300 is equal to 1 over 25, because I kept that there, times dt, because I multiplied dt. So dt is in the numerator, w minus 300 is in the denominator. So that's worth 1 point right there, just the separation of variables. Then we integrate both sides. And on the left side, technically, we don't need a u substitution, but I think it might help here to see what to do if I use a u substitution. So I'm going to let u equal w minus 300. And the derivative of u with respect to w would be 1. Maybe I'll just go through all of this. Because derivative of w is 1, derivative of minus 300 is 0. So then du is equal to 1 times dw, or du is equal to dw, which is technically why you don't really need a u substitution, but I thought it might be easier to see why the antiderivative is what it is when I use the u substitution. So this integral on the left is 1 over u, right? Instead of 1 over w minus 300, I'm going to call that u times du, because instead of dw, I'm going to use du. And then on the right side, meanwhile, we still have 1 over 25 times dt. Okay, so on the left, the antiderivative of 1 over u is just ln of u, plus a constant, but I'm not going to add that here because I'm going to do a combined constant on the other side. The antiderivative of 1 over 25 with respect to t would just be 1 over 25 times t plus a constant. And this is a combined constant. Okay, because it was whatever constant would have been here plus whatever constant would have been there all together as one constant. Okay, now that I've got my ln of u, I'm not going to call it u anymore. I'm going to call it w minus 300. And again, the only reason I went through that u substitution was just to make it more obvious why the antiderivative of 1 over w minus 300 is ln of w minus 300. It's because w minus 300 could be thought of as just a u. So it's like this quantity to the first power, right? 1 over u to the first power, which is why the antiderivative was natural log. Had this quantity been to any other power, I would have used a power rule instead of the log rule, okay? But it was to the first power, so the antiderivative is natural log of that whole entire blop, which we call a u, and then we can call it whatever it really is once we figure that out. So it's natural log of w minus 300. Okay, and that equals 1 over 25 times t plus the constant. Now comes the task of trying to solve for w, right? Evaluate w. So I'm going to take e and raise that to both sides. And when I do that, the natural log and the e on the left cancel. I'm left with absolute value of w minus 300. And then on the right side, I have e to the power of 1 over 25t plus a constant. And some of you might remember when we were doing these problems in chapter 5, we would then go, okay, well, when you add powers, you're technically multiplying bases. So this is e to the 1 over 25t times e to the c. But then we recognize that this is some other constant, right? E is a constant raised to a constant gives just some other constant, which we could call c or we could call it k. And then we could recognize, well, k could be positive or negative, right? It's just a constant, could be positive or negative. And then that's what allows us to get rid of the absolute value here around the w minus 300. I'm going to move up here. So now I've got w minus 300 outside of absolute value equals k times e to the 1 over 25 times t, or to the t over 25. Okay, now before I fully solve for w, I think I'm going to go ahead and do my initial condition here because I need to solve for k. So I'm going to plug in my initial condition, which is 1400 for w and then 0 for t. And just to quickly remind you, that was what they told us to do in the problem. It said find the particular solution with the initial condition when t is 0, w is 1400. So I'm going to plug those values in here and get this. 1400 minus 300 equals k times e to the power of 0, because 1 over 25 times 0 is still 0. 1400 minus 300 is 1100. K times e to the 0 is just k times 1, which is just k. So basically k is equal to 1100. So now I know that w minus 300 is equal to 1100 times e to the 1 over 25 times t. And then from there, to get w completely by itself, all I would have to do is add 300 to the other side. And so then my final answer would be w of t. So w as a function of t is equal to 1100 times e to the 1 over 25t plus 300. That is our final answer for the particular solution w with the given differential equation and initial condition. So let's check scoring guidelines on that as well. So they awarded 5 points to this part total, and you get 1 point for separating the variables. That's always true. You get 0 points if you forget to. So always make sure to separate. And that was when we moved the w minus 300 to the denominator of the other side where w was. We kept the constant, and then we moved dt over to that side. So that part was worth 1 point. Then we took the antiderivative of each, ln of w minus 300, and then 1 over 25t plus the combined constant. So 1 point for both antiderivatives. So that's like a half each. 1 point for just adding plus c. So suppose you had gotten the antiderivatives wrong, you would miss out on this point, but you'd still get the point for separating and the point for adding c, which is cool. It's a way to pick up points. So just take some antiderivatives, even if you're not sure, just write something down and then write plus c, and you've gotten 2 points out of 5, which is pretty good. Okay, then, but if you forget to add c, there's no way you can get any more partial credit. So let's say you did separate correctly, you did get the antiderivatives right, but you forgot to add plus c on the same line when you took antiderivatives. You could only get a maximum of 2 out of 5. So always remember, separate and add c. Okay, so then in the order that they did was, at this point they went ahead and found the condition. They found k, or c, whatever. They plugged in the 1400 here and the 0 there and found that c was ln of 1100, because it'll be different at different stages in the problem solving process. And then they got this w minus 300 is equal to 1100 e to the 1 over 25t, which is what we got. And then they added the 300 over, and the order of addition doesn't matter. So that's how you get the full 5 points.